Section 11.8 of your textbook discusses buffers. There are 3 important questions that you should be prepared to answer on a quiz or exam over the topic of buffers. Let's go through them. The first is, what is a buffer? Just a simple definition. A buffer is a solution that resists changes in pH, or it maintains a fairly constant pH. That's another way of explaining or expressing that idea. A buffer is a solution that resists changes in pH. It does this by neutralizing small amounts of added acid or base. So in order to understand how a buffer works, you need to understand this neutralization aspect that is part of the buffer. If you added acid to any regular unbuffered system, the pH would drop rapidly because of the hydrogen ions present in the acid. If you added base to any unbuffered system, the pH would increase rapidly because you added hydroxide ions from the base to the system. But a buffer will resist change in pH because it is able to neutralize small amounts of either added acid or base. What is a buffer made out of? All buffers contain 2 substances, which are conjugate acid-base pairs of each other. And note, both of these must be present in major amount in order for the buffer to be able to defend or protect against either added acid or added base. So we're looking at 2 substances, and not surprising, these substances are themselves acids and bases. Specifically, they are conjugate acid-base pairs. So the acid portion of the buffer is able to neutralize added base. The base portion of the buffer is able to neutralize added acid. Let's illustrate how a buffer system could work using as an example acetic acid and its conjugate base acetate ion, which forms a buffer system. Now note here that acetate is a negatively charged ion. Charged ions, either positive or negative, cannot exist stably by themselves. So if you need a significant source of acetate ion, you're going to have to obtain that in the form of a salt. And I should add here that the salt needs to be a soluble salt. It has to dissolve in solution. Buffers exist in solution. So you would need a soluble salt that contains the acetate ion. Now, fortunately, acetate ions in salts themselves form soluble compounds. All acetate salts are soluble. But regardless of the anion, if you counter with a cation, such as sodium or potassium, if you put that with a weak base, acetate, you will form a soluble salt. So one more time, the acetate ion needs to be obtained in the form of a salt, a neutral compound. So countering the acetate ion, pairing it up with a sodium ion or potassium ion will make sure that you have a soluble salt because all group 1 cations are soluble. How does a buffer work? Question 3. How does a buffer work? The weak acid part of the buffer neutralizes added base. Therefore, as I mentioned, when you add the base, weak acid neutralizes it in the buffer and the pH doesn't increase greatly. The weak base part of the buffer neutralizes any acid that could be added and keeps the pH from dropping greatly. So let's illustrate how the buffer works using this acetic acid acetate buffer or acetic acid sodium acetate buffer, which is how you would obtain the acetate ion. So how does the buffer work? If we were looking at an acetic acid acetate buffer, if you added strong base to the buffer, a strong base would either be sodium hydroxide or potassium hydroxide. In other words, bases are associated with hydroxide ion. Anything that's able to furnish a large amount of hydroxide ion would rapidly change the pH of the buffer, but the buffer is going to resist that change because the weak acid part of the buffer can neutralize the strong base. In other words, neutralize the hydroxide ion. We've already looked at writing neutralization reactions, and I'm going to present it in two different ways. One way is just the balanced molecular equation format, which many students are more comfortable with. The acetic acid is the weak acid part of the buffer. You add a strong base, such as sodium hydroxide, and a double replacement neutralization reaction happens. The hydrogen ion from the weak acid, acetic acid, combines with the hydroxide from the base, and you form water, and the sodium ion and the acetate ion form sodium acetate. So we have neutralized the hydroxide by the hydrogen ion from the acetic acid combining with it to form water. The net ionic equation is actually the clearer, cleaner way of explaining the chemistry, which is why we discussed net ionic equations. So if you look at this reaction and write the net ionic equation for it, you will see that the hydrogen ion from the acetic acid combines, all right, is donated to the hydroxide ion, and you make water plus acetate ion. So the weak acid, acetic acid, neutralizes the hydroxide ion, and water is formed, as well as acetate ion, which is a weak base. So you've taken a strong base, hydroxide, and converted it into a weak base. The pH does not change much. It only would increase by a small amount, just a small amount. So the explanation, the weak acid in the buffer, acetic acid, is able to neutralize or donate a hydrogen ion to the strong base, sodium hydroxide, for example, or specifically hydroxide ion. A weak base is formed, in this instance, acetate ion, which doesn't change the pH very much. It would only increase by a very small amount, staying fairly constant. Let's look at the other possibility, which is that you add strong acid to the buffer. Now, if you added strong acid, that could be in the form of hydrochloric acid or nitric acid. We recognize these as strong acids. Basically, anything that is able to furnish a large amount of hydrogen ions. What happens if you add strong acid to the buffer? Well, the weak base component of the buffer, in this instance, the acetate ion, in the form of a salt such as sodium acetate or potassium acetate, is going to neutralize the strong acid. So looking at this neutralization reaction between hydrochloric acid, for example, and acetate in the form of sodium acetate, double replacement reaction, the hydrogen ion from the hydrochloric acid combines with the acetate ion to form acetic acid, and then sodium chloride would be your other product. So the hydrogen ions from the strong acid are sponged up or combined with the acetate ion to form a weak acid, acetic acid. Again, the net ionic equation is a cleaner, clearer explanation of this. Here is the hydrogen ion from the strong acid. The acetate ion combines with the hydrogen ion to form acetic acid. So acetic acid, a weak acid. We are recognizing that both the sodium and chloride are spectator ions and would cancel out in the net ionic equation. They would not be appearing, just like the sodium ion is a spectator ion and would not appear in the net ionic equation for the previous reaction we looked at. So, explanation, the weak base in the buffer, the acetate ion, is able to neutralize, in other words, accept a hydrogen ion from the strong acid. Hydrogen ion is accepted by the acetate, and the weak acid, acetic acid, is formed, which doesn't give up the hydrogen ion readily, and therefore the pH decreases by only a small amount. So notice when buffers are working, one component of the buffer, when it is doing its job, such as acetic acid neutralizing base, it converts into its conjugate pair, the acetate ion. When acetate is functioning in the buffer to neutralize hydrogen ion, it converts into its conjugate pair, acetic acid. So since acetic acid and acetate ion each are weak acid, weak base, when they are formed, the pH does not change significantly. Therefore, you've taken a tiger, right? You've taken something that would cause the pH to change greatly, either hydrogen ion or hydroxide ion, which would greatly change the pH. And you've taken those tigers and converted them into, I like to say, pussycats. In other words, substances in solution that act as either a weak acid or a weak base and do not change the pH very much.